Okay, so the next one is 15. In this one we have to use the result of exercise 14 to prove that if E is a linear operator whose square is equal to itself, then it is diagonalizable. So let us recall the result of exercise 14. In exercise 14 we had a linear operator on V, all of whose characteristic roots lie in F. Then it is diagonalizable if and only if the following implication is true. What implication? If this is equal to 0, then the t minus lambda image of V is also equal to 0. For any V in the vector space, any scalar lambda in F, and any positive integer n. So we have to use this to prove that our E is diagonalizable. That means we now have to verify that this implication is true for E. Okay, so that's how let us start the solution. We should, however, not also forget the fact that this is only for operators T that have all their characteristic roots in F. Is that true for E? We are coming to that later, okay. We claim that for any vector V, any scalar lambda, and any positive integer n, the following implication is true. Implies this is equal to 0, and we are going to treat this as a statement. I mean, if it is a statement after all, a statement about M, and we are now going to establish this claim by induction on M. The claim is trivial when M is 1. Why? Because if M is 1, then this side of the implication, the hypothesis of the implication is just the conclusion itself. So if that is true, then automatically this is also true. Assume the claim, that is, assume that the claim is true for some positive integer n. Now, let V be some vector in V and lambda be some scalar in F, such that V E minus lambda to the power m plus 1 is equal to 0. Okay. So what is our aim now? We now want to prove that the E minus lambda image of V is also equal to 0 under the assumption that this is true. Alright. But also do not forget that besides having this, we also have our induction hypothesis, namely that the above implication is true for that specific M, but at the same time one should not also forget that the implication is true for that specific M, but simultaneously for all V and all lambda. Do you get the point here? If for any V and any lambda this is equal to 0 for that M, then this is also true. That is the induction hypothesis. We want to show that this is equal to 0. Suppose this is not true, then something must go wrong. Must go wrong means we expect something to go wrong. Let's see if we can get anything like that. Suppose this is non-zero. Now we haven't used this thing, so now we are going to use this. Note that V E minus lambda to the power n is V E minus lambda to the power m plus 1, and this of course is 0. So now what can we say from the fact that this is 0 and this is non-zero? Note carefully that when you apply E minus lambda on V, the result is a vector. Now applying this E minus lambda to the power m on this vector, we are getting 0. So by the induction hypothesis, which is true for all vectors and all lambda and that specific m, what should we get now? So by the induction hypothesis, applying this mth power of E minus lambda on this vector, we have got 0. So on that vector, if we apply E minus lambda, then also we should get 0. That is, we should have this. This was our vector on which if we apply E minus lambda, then also we should get 0. This is a result of our induction hypothesis. Okay. In getting this, we did not have to use this supposition, but now we will use. Okay, now what can we say from this and this? We are applying E minus lambda on a non-zero vector and getting 0. This means that the null space of E minus lambda has this non-zero vector, and that is why this is an eigenvector corresponding to the eigenvalue lambda. In other words, lambda is an eigenvalue of E. Since is not equal to 0, lambda is thus, I keep on saying eigenvalue, characteristic root is a characteristic root, because we do not use the word eigenvalue in this book. Now, can we say something about what lambda can possibly be? Yes, we can. And in fact, this is where we are for the first time going to use the fact that E square is equal to E. Now, since E square is equal to E, that means E satisfies the polynomial x square minus x. So, x square minus x is an annihilating polynomial for E. So, the minimal polynomial for E will divide that. Divides this, and that's why the roots of the minimal polynomial for E are either 0 or 1, because these are the only roots of this polynomial. Okay. But we also know that the roots of the minimal polynomial of an operator are precisely its characteristic roots. Hence, the characteristic roots of E belong to, let me put it this way, belong to the set 0, 1. And as a result, this lambda is either 0 or 1. Now, let us see what we get from from these two situations, these two options. If, say, lambda is 0, what shall we get from this equation? Because lambda is 0, we are just applying two copies of E on V. That is, we are having V E square. V E square should be equal to 0. However, at the same time, from this inequality, I can call it inequality because it's not an equation, we also get the fact that V E is not equal to 0. V E square is 0, but V E is non-zero. This cannot be true because E square is just E. So, there you get a contradiction. If lambda is 0, then VE is non-zero, but VE square is equal to 0. But this is impossible. Since E square is equal to E. That means lambda cannot be 0. On the other hand, if lambda is 1, then what are we going to get from that inequality, that V e minus lambda is not equal to 0? From that we will get, in this case, that V e is not equal to V. I mean, if you really apply the operator e minus 1 on V, then you get V e minus V, because 1 is the identity operator. So from that you get this. And additionally, what do you get from that equation? Let me write like this: V e minus 1 e minus 1, this is equal to 0, which is equivalent to having e square minus 2e plus 1 equal to 0. Now we know that e square is e. So e minus 2e plus 1 equal to 0. Oh, and by the way, how did I write this in place of this product? You can use the various laws that you have of manipulating operators, expressions involving operators, or you can just simply use the fact that we have the ordinary binomial theorem in the algebra of operators to expand some power like this, provided the operators that you have commute. E of course commutes with 1, and that is why when you consider, if you just simply do the multiplication, you multiply e with e, that way you get e square. Now multiplying e with minus 1, you get minus e1, but multiplying minus 1 with e, you get minus 1e. These two are just simply minus e. That's why you get minus 2e, and minus 1 times minus 1 is plus 1. Again, do not get confused here, because this 1 is not real number 1. We understand of course what we are dealing with, but sometimes we may forget. Okay, so this is the identity operator, and this minus 1 is the additive inverse of the identity operator in the operator algebra. But anyway, we now have this. If and only if. So e minus 2e is minus e. And now if I just skip one step, I can directly write this. So that straight away clashes with this one, since this is also not possible we have a contradiction. And this contradiction arises because of what? What is the source of this contradiction? Namely, the assumption that V e minus lambda is not equal to 0. It's from there only things have come to this stage. So, our last supposition, you may want to give some number to a supposition which later you want to show is wrong, so that you can refer to it and say that this supposition is not true. But it's always a good idea to just simply write our last supposition is wrong. Okay, you will see that in any type of proof, if you are supposing something and anticipating that it will be wrong, it will always be the last supposition. i.e. we must have but this is what we wanted to show, and so this is our induction step. Thus, the claim has been established by induction. Oh, and the issue of the possible eigenvalues of E. You can clearly see that since the minimal polynomial of E has to divide this polynomial whose roots are 0 and 1. So, the possible eigenvalues are 0 and 1, and of course, both of them belong to the underlying field, no matter what field we are considering, even when F is the smallest field possible, which has only two elements 0 and 1, still there 0 and 1 are there. So, we can just simply now write. It has become clear in the course of proving all these things that the possible eigenvalues of E belong to F. Hence, by the result, and as a result we can apply the result of problem 14. E is diagonalizable. Okay. Next, 16. If E is an operator whose square is itself and F is also an operator whose square is itself, prove that E and F are similar if and only if they have the same rank, that is, their range spaces have the same dimension. Now here the solution is extremely easy. E and F are both diagonalizable because of the previous exercise, and that is why E and F are similar, and moreover the possible eigenvalues of them are 0 and 1. So all these facts already are there with them, if and only if the multiplicities, and because of all those things, multiplicities of 1 as a characteristic root of them are equal, and this multiplicity actually is the rank of these operators, and that is why we continue with if and only if they have the same rank. If you are still a little doubtful about how this is a solution, I suggest you go back and see this. See exercise 24 of the third section of this chapter. Just a look at that exercise will make everything clear. So that's just it, that is 16. Next, 17. If the multiplicity of each characteristic root of T is 1. So each root appears as a characteristic root precisely once, and additionally all the characteristic roots of T are in F, are in the underlying field. Prove that T is diagonalizable. Now for this also we do not have to do anything at all, because whatever we need to have this claim have already been done here. See the solution to exercise 40. That solution which we did in the previous video. The last part of that solution itself has the answer to this. Okay, so from that solution itself, it automatically follows. And finally, let's see the next one also. Actually, there are two more, besides the next one, but we will do those things in the next video. 18. Let the characteristic of a field of F be 0. So F is a characteristic 0 field. Let T be a linear operator on V over F, and let this satisfy the relation that the mth power of T is equal to 1. 1 of course means the identity operator, and m is some positive integer. Although it is not mentioned explicitly that m is a positive integer, but it is understood. If the characteristic roots of F of T are all in F, then prove that T is diagonalizable. Okay. Since this relation is satisfied by T, that means T satisfies the polynomial x to the power m minus 1, and so the minimal polynomial of T will divide this polynomial. So we see that polynomials keep helping us in studying linear algebra. Polynomials help us means polynomial ring helps us. So ring theory is there in the background always. For T over F, that's understood, divides this. Now this polynomial has only distinct roots, since the roots of this in any field, any field means any field of characteristic 0, are distinct. So the roots of the minimal polynomial for T, whatever it is, will also automatically be distinct, because those roots will be among these roots, the roots of this polynomial. The multiplicity of each characteristic root of T is 1. Combined with this, the fact that the characteristic roots of T are all in F, so by the previous exercise, T is diagonalizable. Hence, T is diagonalizable. But there may still be a doubt. Exactly how is it true that the roots of this polynomial are distinct? Let us see. And to see why, you have to recall what we saw in field theory. Suppose forcefully that this polynomial has a multiple root. Multiple root means a root whose multiplicity is more than 1. Say that root is R. Then recall from field theory that in that case, if you substitute R for X here, you will get 0 because it's a root. But at the same time, because its multiplicity is more than 1, if you substitute R in the derivative of this polynomial, then also you should get 0. Now, what is the derivative of this polynomial? We see that in spite of dealing with a general polynomial over any type of field, the derivative still continues to be the ones that we know from calculus, because that's how the derivative was defined in fact. Now, from this, by substituting x equal to R here, what do we get? We get this. Okay, because this polynomial should be satisfied by R, but the derivative should also be satisfied by R. So we have to simultaneously get this. Now note the fact that m is a positive integer, alright. So m is a positive integer means this has to be 0, and so no other choice but to have r equal to 0 and also at the same time m greater than 1. Okay, so that thing is also there. That means r has to be equal to 0. Why? Because we are in a field, right? We are in a field, and so see, the fact that you can cancel m from here is not simply because of the fact that m is a positive integer. Do not forget, in fact I myself forgot just now, that we are not dealing with real numbers, we are dealing with field elements. Since the field has characteristic 0 and m is a positive integer, so m times anything will be 0 only when that thing itself is 0. Otherwise the field will have finite characteristic. In a field of characteristic 0, that never happens. You add a non-zero something to itself any finite number of times, you are never going to get 0. So that's how we get 0, and that's where the fact that f has characteristic 0 plays a role. But then we have to have this, since every field is an integral domain, so 0 divisors do not exist. But if you now use the value here, obviously you are going to get 0 on the left hand side, but the right hand side is 1, and in no field do you have 0 equal to 1. That's a contradiction, and that contradiction arises from our forceful supposition that this has a multiple root. So this does not have a multiple root, and this is where this part plays a role. Okay, so let's just end the video here itself. Tomorrow is Sunday, right? So we as usual have our analysis. Okay, so see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.